So I did it again. I forgot to record, and we've been going for about 15 minutes. But in the first part of this, I went over, I just briefly went over IR spectroscopy. And then we went over chapter 14. We talked about the two main reactions that are in chapter 14, namely electrophilic addition to dienes and the Diels-Alder reaction. Oh, you can see that all right here. And then we moved into chapter 15 and 16. Chapter 15, we said, is about aromaticity. And we went over, we mentioned the Huckel rules, that these are what help us to determine whether a molecule is aromatic or not. And there's some pretty detailed instructions in chapter 15 class notes that show you how to determine whether a molecule is aromatic or not. For example, 10-annuline is one compound we talked about in class. We said this is a molecule that has 10 pi electrons, and it's cyclic, and it's conjugated. So the only thing that prevents it from being aromatic is that it's not planar. And we reviewed how you can tell it's not going to be planar because of these two hydrogens that point in the middle that are basically right on top of each other. I can't even really draw them properly in ChemDraw. But that prevents the molecule from being planar. So that's why 10-annuline is not aromatic. It's not planar. And we use this method to go over aromatic heterocycles, aromatic ions. And we used it to tell pretty much whether a molecule is aromatic or not. And then in chapter 16, we started going over that as well. This chapter is showing us finally what aromatic compounds do. We know that benzene is not an alkene, but benzene is special, as are the other aromatic compounds, though I think we'll mainly use benzene when it comes to reactions. And we said that benzene does not undergo electrophilic addition reactions like alkenes do. We learned that back in chapter 8 in Organic 1. Benzene does not undergo reactions like that. Rather, benzene undergoes electrophilic substitution reactions. And we said, for example, how benzene will react with chlorine and aluminum chloride to give chlorobenzene, or with nitric acid and sulfuric acid to give nitrobenzene. We also talked about directing effects. We said if you chlorinated nitrobenzene, you would get the meta-chlorinated product because the nitro group is meta-directing. And we went into some detail in chapter 16 about why that is. Whereas, for example, if instead we used anisole, which is methoxybenzene, then we'd expect the major product to be the para-substituted chlorinated product. And there are lots of other reactions of aromatic compounds that are in this chapter. The Friedel-Crafts reactions. And we learned their mechanisms. Went into some detail about that. Should we know the mechanisms for the final? All of the mechanisms from the whole semester are fair game. I'm not going to say exactly which mechanisms are on the exam. So yes, you need to know the mechanisms for the final. The final is cumulative for the whole semester, with maybe some emphasis on chapters 29 and 31. Here we're going over ortho-para directing groups, which we talked about. Now, do you want me to go over one of those mechanisms? It's a little hard on ChemDraw, but I can try. No fair saying only go over the mechanisms that are on the exam. That's not fair. I don't think I remember them anyway. These are not mechanisms. This is explaining why para-directing groups are para-directing or ortho-para-directing, and why meta-directing groups are meta-directing, which we talked a fair bit of theory on. And lastly, we ended up with multiple substituent effects. There are certainly other reactions of aromatic compounds like nucleophilic aromatic substitution. Main thing to be aware of with both electrophilic and nucleophilic really just with nucleophilic aromatic substitution, now that I think, is that the reaction is neither SN2 nor SN1. And we went over the mechanism of nucleophilic aromatic substitution, also the benzyne reaction. And then ended the chapter with redox reactions of aromatic compounds. We talked about alkyl benzenes. For example, we said that if you treat pretty much any alkyl benzene, as long as there's at least one benzylic hydrogen, the other two bonds can be to anything. But as long as there's at least one, then this reacts with potassium permanganate. In water, and the product that you get is the carboxylic acid. We talked also about hydrogenation of benzene. We talked about halogenation at the benzylic position. And that was pretty much it for chapter 16. Now 17 and 18 were in organic 1. So that gets us to chapter 19. And chapter 19 was a big chapter with a lot of really important mechanisms. All of these reactions basically involved nucleophilic addition to carbonyl groups. Well, we'll just do this. So we talked, for example, about Grignard addition. To ketones and aldehydes. Really, this is first the Grignard reagent. Followed by, you do need an aqueous workup. Either water or dilute H3O plus. And I forgot the OH. Other than that, it's perfect. There, that's more like it. We talked about addition of amines. And we said, for example, that addition of a primary amine in the presence of an acid catalyst will give you the imine we said that addition of a secondary amine oops. That's better. Will give you the enamine as long as there's at least one alpha proton. And last but not least, we said that addition of an alcohol will give the acetal. Ethanol is the solvent, so there's an excess of it. Those really were the main reactions in this chapter. I feel like I should review one of these mechanisms, but maybe it's in the class notes. I think they are. Yes, all these mechanisms are in the class notes. This is the mechanism for forming the enamine. This is the mechanism for forming an acetal. So the way this works is by protonation of the oxygen with the conjugate acid of the alcohol that you're given. Here we're using cyclohexanone and methanol with an acid catalyst. Generally, these do require heat also. It's best practice to mention heat, but the problem might not mention heat. So then you get this intermediate. This is now ready for nucleophilic attack, so the alcohol attacks. That gives this intermediate, and remember, after nucleophilic attack, we have proton transfers. So first thing we need to do is pull a proton off of this oxygen to get rid of the plus charge using the alcohol. That gives this intermediate. Then we need to protonate this oxygen so that we can lose water as a leaving group. That's the main goal of the reaction, is losing water as a leaving group. So we pick up a proton from the conjugate acid, and then the molecule loses water with help from one of the lone pairs on the alkoxy group that's now already installed. And we get what looks very similar to this intermediate, except instead of OH, it's O-alkyl. Other than that, it's the exact same thing. And we're already used to that undergoing nucleophilic attack. And after nucleophilic attack, we have proton transfer. So we pull off this proton in order to get rid of the plus charge, and you get your acetal. This mechanism also applies in chapter 25, where we learned about going from a hemiacetal to an acetal in the context of sugars forming a glycoside. Wittig reaction. And we also covered conjugate addition in this chapter. We learned that some nucleophiles, when they're reacted with an alpha beta unsaturated ketone or aldehyde, prefer to add to the beta carbon. And they're listed over here in the chapter. Water, the cyanide ion, primary and secondary amines, cuprates, and enolates. At the time, we didn't yet know what an enolate was, but now we do. And then there are those nucleophiles that prefer to add directly to the carbonyl, like this. That would include your Grignard reagents, alkyl lithium species, hydride reagents, prefer to add directly to the carbonyl carbon. And we gave an example of a conjugate addition in the class notes. So this edition of the class notes has all of the mechanisms in there. Well, maybe not cyanohydrin formation. But the mechanism of cyanohydrin formation is just the same as the mechanism of a Grignard reaction. So those are the main points in chapter 19. Chapter 20 was a shorter chapter. It was basically on carboxylic acids and nitriles. And one thing we spent some time on in this chapter is the acidity of carboxylic acids. So for instance, is it okay if I abbreviate a carboxylic acid functional group as CO2H, just to save some time? We said that anything that makes the conjugate base more stable makes the acid stronger. And the conjugate base is going to be, of course, CO2 minus on all of them. So you just take away the hydrogen to get the conjugate base. And the question is, what's the effect of putting different groups onto the aromatic carboxylic acid? Which of these then will be the strongest? So let's say that, oh, my cat's meowing. That's just too bad for him. So if we were to label these in order from strongest acid to weakest acid, the strongest acid is going to be the one that removes the most electron density from CO2 minus when you make the conjugate base, because we want to spread out that electron density that you get from there. And so we want groups on the benzene ring that will remove electron density. And the one that's the best at that is the nitro group. The one that's second best at that is the chlorine, because it's quite electronegative. So I think that will be next. And then comes just unsubstituted benzoic acid itself, whereas the weakest acid is going to be the methoxy substituted compound, because the methoxy is quite electron donating. And so that will pile more and more negative charge onto the conjugate base. So that's going to be the weakest acid. Remember, the goal is to withdraw electron density from the conjugate base. And the nitro group's the best at that. So if I were to rank those four compounds in order, from strongest acid to weakest acid, that's how I would do it. It's essentially chapter 20, section 4. We talked about some ways of making carboxylic acids. We already talked about one of them, oxidation of alkyl benzenes with permanganate ion. And of course, you can make them by oxidation reactions. Those we talked about in chapters 17 and 19. Mostly chapter 17. Then we talked about hydrolysis of nitriles. That's another way to make a carboxylic acid. Just so you see what it's talking about. Hydrolyze a nitrile, and you'll get the corresponding carboxylic acid. And we also talked about carbonation of Grignard reagents. We went over that mechanism. It's the same as the mechanism of the Grignard reaction. And then we talked about reactions of carboxylic acids, which there aren't that many, because carboxylic acids are the least reactive acyl derivative. One of the main reactions is deprotonation by even a moderate base, and then doing an SN2 reaction. This is a way of making an ester. So you can review about that back in chapter 11. It's just an SN2 reaction. A lot of these came from chapter 11 and chapter 17. But they left the main topics of nucleophilic acyl substitution and alpha substitution to chapters 21 and 22. Similarly, in order to make a nitrile, one of the best ways is by an SN2 reaction. I'll give you an example. Take 1 iota propane. Treat it with sodium cyanide. and you will get butane nitrile. By the way, don't forget that a nitrile is a triple bond in it. Right? Don't forget what the structure of a nitrile is. So you wind up with a nitrile that's one carbon longer than the alkyl halide you started with. Or dehydration of a primary amide with thionyl chloride or phosphorus oxychloride. Specifically says you're not responsible for that mechanism. And here we have about hydrolysis of nitriles. We don't really cover that completely until chapter 24. Or was it 21? We'll find out. And of course, you have all the reactions listed at the end. So that's chapter 20. Chapter 21 was again another big chapter. This is on nucleophilic acyl substitution. So these are reactions of this type. Where the group Y is a leaving group. So you get substitution products. I don't know why it's giving me that red border there. So for this chapter, you need to know all of your functional groups, which you need to know anyway. And we said the order of the reactivity in terms of Y starts with carboxylic acids as the least reactive acyl derivative. So this is order of acyl derivative reactivity from least reactive to most reactive. So it starts with carboxylic acids. Then let's see, I believe amides are next. Yeah, that sounds right. Then esters come next. Followed by thioesters, which we really only met in chapter 29. Followed by anhydrides. Followed by acid chlorides. And that's why it's so good that we have a way of converting a carboxylic acid to an acid chloride. And the reagent of choice for that is thionyl chloride. So that's a very useful reaction to remember. That allows you to convert the least reactive carboxylic acid derivative to the most reactive one in one step. Oh, there it is. And we talked about Fischer esterification. Finally, we went over the mechanism after mentioning this in several previous chapters. So the mechanism's in your class notes. You might as well go over this one. So we take our carboxylic acid and dissolve it in an alcohol with an acid catalyst. So you have some of the conjugate acid of the alcohol present. First step in acidic medium, I hope this has come across this term. First step in acidic medium, protonate the carbonyl oxygen. So we use the conjugate acid in order to put the proton onto the oxygen. That gives us this intermediate over here. Then after protonating the oxygen, nucleophilic attack. So we use the alcohol we're given in order to attack that carbon, break the pi bond, and give this intermediate. After nucleophilic attack, proton transfers. So first thing we're going to do is pull the proton off of this oxygen to get rid of the plus charge. That gives us this intermediate. And then we want to put a proton on either of those two OHs. It doesn't matter which one, they're the same. And that gives us this intermediate. Again, we use the conjugate acid of the given alcohol in order to do that. So after that, the molecule loses water. That's the whole point of this reaction, is losing a molecule of water. One of the oxygens donates an electron pair in order to do that. I think it makes the most sense to use the OH oxygen in order to kick out water as a leaving group. That gives us this intermediate. And then finally, the alcohol deprotonates the oxygen to give your neutral ester as the product. (21.4) is probably the main section of this chapter, I would say, the one that's the most important, because that section is referred to quite a few times in subsequent chapters. In fact, we referred to it today. So acid chlorides can react with alcohols in either acidic or alkaline medium in order to give esters. Acid chlorides can react with amines. Here's an example over here in order to make an amide. Mechanism is essentially identical, just uses an amine instead of an alcohol. And you wind up with converting the acid chloride to an amide. And acid anhydrides react pretty much like acid chlorides do. They're just a little bit less reactive, but not very much. Then we went over chemistry of esters. We talked about the mechanism of acid hydrolysis of an ester. That's given here in your class notes. It's essentially just like Fischer esterification, except backwards. It's absolutely step for step the reverse of hydrolysis. Of Fischer esterification. So that's hydrolysis of an ester in acidic solution. And then we looked at the mechanism in alkaline solution. I find the alkaline solution mechanisms have fewer steps. Main feature here is you actually wind up making the carboxylic acid product in alkaline solution. So you need to show your base pulling off that proton. This is a very common mistake on exams. But the base pulls off that proton and gives you the carboxylate ion. And that's what's going to be in solution until you acidify. So you add your H3O plus. The first thing the H3O plus does is neutralize the leftover base. And then it starts putting the proton back on the carboxylate. And you get the carboxylic acid. So the mechanism always looks more straightforward to me in alkaline solution. And of course, we're just getting into polymers now. We finished it in the Tuesday-Thursday class on Thursday. And we're starting step growth polymers. We started that today in the Monday, Wednesday, Friday class. And then, last but not least, the mechanism of nitrile and amide hydrolysis. This is worth looking at. Main thing to notice is if you learn the mechanism of nitrile hydrolysis, you get the mechanism of amide hydrolysis thrown in for free. So you might, for instance, be asked to hydrolyze an amide. Well, the first thing you would do in acidic solution is protonate the carbonyl oxygen. And then from here on in, it's just like hydrolyzing an ester. Main thing to watch out for is protonation of the nitrogen, because we want to lose ammonia as a leaving group. And that results in formation of the carboxylic acid. We also have on the next page, it's a little bit small on the screen, but amide hydrolysis in alkaline medium, also worth looking at. And what you notice is when you get halfway through hydrolyzing the nitrile, lo and behold, you make an amide. And so the mechanism of alkaline hydrolysis of an amide starts with hydroxide attacking the carbonyl carbon, just as we're used to seeing in alkaline solution. First step is going to be nucleophilic addition. Then comes protonation of the amine, because we want to lose ammonia as a leaving group. Then loss of ammonia as the leaving group. And finally, notice again, we have deprotonation of the carboxylic acid in alkaline solution. You have to show this step. Otherwise, the mechanism is not complete, because you can't prevent the deprotonation of the carboxylic acid. It's going to happen in alkaline solution. That gives you the carboxylate ion, which after acidification gives you back the carboxylic acid. So all those mechanisms are in your class notes. Gosh, that was only chapter 21. Chapter 22 is carbonyl alpha substitution reactions. And the main thing we learned here is what is an enol and what is an enolate. So here's our carbonyl compound. Whoops. The enol form looks like this. And these two are in equilibrium with each other. Where's my equilibrium arrow? With the keto form being almost always more stable than the enol form. And then we also learned about the enolate. The enolate ion being a resonance stabilized species. Now we do not use an equilibrium arrow, we use a resonance arrow. So this species, whichever way you draw it, is an enolate. And we discussed alpha substitution, both of enols and of enolates. Alpha halogenation of aldehydes and ketones was one reaction we talked about. And we went over the mechanism. Then we talked about enolates and reactivity of enolate ions. We said enolates are really good nucleophiles. They can undergo a reaction with either a halogen or an alkyl halide. So for example, if you treated this enolate with benzyl bromide, that's a really good electrophile. Then you will get an SN2 reaction. And you will get this product. And we talked about the haloform reaction. I think that reaction made its way onto a past exam. And we ended up with the acetoacetic ester synthesis and malonic ester synthesis. And I'm sorry, I need a quick bathroom break. Okay. So this type of reaction is the basis for the acetoacetic ester and malonic ester syntheses. And the mechanisms are in the class notes. Then brief mention of kinetic versus thermodynamic enolates. And with that, we're already in chapter 23, which should be pretty familiar since this was on the previous exam. This was about the aldol and Claisen condensations and their variants. And we also talked about Michael additions, which we really had already gone over in chapter 19. The first sections up until 23.6 really are all on aldol reactions. They're all the same, it's just variations on it. Like here we had a mixed aldol reaction, same mechanism. Here's an intramolecular aldol reaction, same mechanism. The Claisen condensation is basically an aldol reaction with esters. And the mechanism is real similar to the aldol condensation, except that there's no possibility of dehydration. You don't even have to worry about that. And as I'm sure you'll recall, since we just recently had it on the exam, aldol reactions almost always go with dehydration. I think in active, they emphasize the aldol addition reaction a little too much. It's really hard to get an aldol reaction to go without the loss of water. And lots of times, you can't even prevent the loss of water, even if you want to. And we covered a typical Michael reaction. That mechanism is also in your class notes. It shows formation of an enolate, and the enolate adding to the beta carbon of an alpha beta unsaturated ketone to give another enolate, which simply pulls a proton off of the solvent. Just look back at what you're given. You're given ethanol as the solvent. And then another one of these pesky cases where there's an acidic hydrogen in the presence of base. So you can't prevent the base from pulling that proton off. It's gonna happen in order to give you this enolate again. And then after careful acidification, we don't want to hydrolyze our ester. That puts the proton back on and gives you this compound back. Howdy, speaking of this past exam, do you have an estimate of when the Tuesday, Thursday classes will get their results? Thank you so much. I really hope tomorrow. One of my graders hasn't shown up and I'm a little worried. But I know you want that before you take the actual exam, so we're going to try our best. Oh, if something goes wrong and I can't get it up, then can't get the exam results, then I'll at least put up the exam in the answer key so you can see that. But I really had intended for it to be done tomorrow. Anyway, then we talked about the Stork-enamine reaction. And that's just another example of a Michael addition. We basically said enamines react just like enolates do. And there's your mechanism of iminium hydrolysis. Robinson annulation is pretty special. You have to have it set up just right in order for it to work. But we gave an example of one of those also in the class notes. And again, a list of reactions. All right, chapter 24 is on amines. We actually covered it a long time ago. Talking about the relative basicity of amines. And we got into synthesis of amines. We talked about reduction of nitriles and reduction of amides. So we said, for example, that you can take a nitrile treat it with lithium aluminum hydride and diethyl ether solvent, followed by an aqueous or aqueous acid workup. And you will get the corresponding primary amine. As usual, corresponding, meaning that it has the same number of carbons as what we started with. And amides can be reduced to amines also. Darn, the Gabriel synthesis isn't in your class notes. Well, the Gabriel synthesis of amines was the one that started with phthalimide. First, we had deprotonation of the imide nitrogen, the NH group. And then treatment with any alkyl halide, preferably primary. Really want to draw it like this. Whatever halogen you like, this then undergoes an SN2 reaction. And you get the substituted amine. And then, last but not least, the third step is hydroxide again. I really should have numbered these steps. And that cleaves out the amine. And gives you phthalate as the byproduct. In other words, the rest of the aromatic ring. We really don't care about that. We care about the major organic product, which is the amine. And that's a good way of making amines. This chapter had both the Hofmann rearrangement and the Hofmann elimination, which is unfortunately confusing. And we gave the Hofmann rearrangement mechanism. Talked briefly about aromatic amines undergoing diazonium couplings. And that was pretty much it for chapter 24. And after that, it got into the biochem chapters. I guess I didn't mention NMR. NMR was also on this past exam. Once again, there's not going to be spectroscopy problems like you had on this last exam, but there could be questions about proton NMR or carbon NMR spectroscopy. Example. What is the splitting pattern of the methyl groups in isopropanol? A, 2H doublet, B, 6H doublet, C, 2H quartet, D, 6H quartet. Something like that would be a fair game question. Or where would the carbon atom, that's alpha to oxygen, show up in carbon NMR spectroscopy? A20, B40, C70, D 110 parts per million? That would also be a perfectly reasonable question. One of the most common questions I get is if I have any multiple choice questions for you to practice on. I do not. I don't have a bank of multiple choice questions. You can expect that some of them will be conceptual. There may be some of them that involve reactions. Some of them are really easy, others are significantly harder. And I don't think it's more than it's certainly significantly less than half the exam, significantly less than half. That's multiple choice. I made the exam to be a reasonable length to be doable within an hour and a half, and you have 2 hours. So finishing in general has not been a huge problem. So chapter 25 we just had recently, that was on carbohydrates. So that was on the previous exam. We focused really on glucose. That was one of the few compounds you needed to memorize the structure for. We focused on drawing glucose and other similar compounds in the straight chain form, in the chair form, and in the Pyranose-Hayworth projection. You didn't need to know the Pyranose form, and still don't. And we went over some reactions of monosaccharides, exhaustive alkylation, exhaustive acylation, glycoside formation. There's the mechanism. It's the same as in chapter 19. It's just going from a hemiacetal to a full acetal. And some other reactions of monosaccharides. And I think we ended up with the Kiliani-Fisher synthesis and the Wohl degradation. And then, of course, how to draw disaccharides. And that was pretty much it for chapter 25. Chapter 26, I think, was polypeptides. Yes, the main thing we focused on here was drawing a small polypeptide, say 2 or 3 amino acid residues. And also the effect of pH on the structure of these things. So here's an example. You had a question like this on the exam. And we learned how to draw them with correct stereochemistry. As you see, it gave you the side chains. I don't expect you to memorize those. And last of all, we talked a little bit about the strategy of making a dipeptide. You can't just throw 2 amino acids together and hope for the best. You're going to get a mixture. So we talked about protecting one of the amino groups, protecting one of the carboxylic acid groups, and then coupling them with DCC. That's pretty much the strategy. This is fully automated today, controlled by computers and automated on solid phase. So you can make, in principle, whatever polypeptide you want. Chapter 27 was on lipids. Main thing we talked about here was how to tell the different types of lipids one from another. How do you know if it's a fatty acid, if it's a wax, if it's a soap? If it's a phospholipid, if it's a prostaglandin, if it's a terpene, if it's a steroid. And we had a little matching section on that exam. Fatty acids themselves are in many ways nothing special. They're just carboxylic acids with a really long chain. So I feel like this was also pretty recent. This must have been on exam 3. But there wasn't really much else in that chapter that we talked about. That was the main thing. Certainly anything like draw cholesterol, no, nothing like that. Chapter 28 was even earlier in the term, I think. That was on nucleic acids. The main thing we talked about here was drawing a small polynucleotide or oligonucleotide. So for example, draw a guanine nucleotide of the type found in DNA. That would be a reasonable question. And so we start with, I always start with the sugar. Which in this case will be 2-deoxyribose. We have CH2OH over here at the so-called 5' end. We have an H on carbon 2 because it's deoxy. OH over here. Now I just need my guanine. That's not right. There we go. Something like that. And that only leaves chapters 29 and 31, which we just did. In chapter 29, the main thing to know is not all of the pathways. You do not have to memorize all the pathways. Rather, focus on recognizing reaction types. And I made a set of practice problems for you, and I put the answers. So for example, on this one, always look for the part of the molecule that's changing. We're going from a ketone to a secondary alcohol. I would expect you to recognize that as a reduction. Or over here, we have an extra CO2 minus that's gone in the product. So that would be a decarboxylation. And I did give you a word bank. So that's the main thing to focus on, is recognizing types of reactions. They're all reactions we talked about either in Organic 2 or Organic 1. Most of them in Organic 2. And then finally in chapter 31, focus on drawing polymers, drawing the structures of polymers. And I gave you a worksheet where I gave you the monomers. Here's 4 addition polymers that you'll get. Then we have some condensation polymers. This one would give a polyamide or a nylon. This one also a polyamide. This one would give a polyester. This one also a polyester. Then we have reaction with phosgene. This is going to form a polycarbonate, as will this one. And then the last 2 will make polyurethanes. So that's the main thing to focus on in chapter 31. And I can't believe I managed to do this, but that's 8 o'clock. So that's a summary of what we talked about this term. Are there any other questions? I don't know what I can answer. So like I said, I'm not going to tell you exactly what's on the exam. I think I've given enough hints already in this review session. I dropped several hints. You can expect there will be mechanisms. You can expect there will be reactions, fill in the product. So I think most of the question formats will be familiar to you. Can you please move the old exam folder? Oh, yes. There you go. And that will, of course, make it onto the video, now that we know we're recording. So we did it rather quickly, but we covered everything. An example of carboxylation, sure. The way you know a carboxylation is you'll see C double bond OO appear, where there wasn't one in the starting material. Like this one. Do you see how there's CO2 minus that wasn't in the starting material? That's an example of a carboxylation, because we've added CO2 to the molecule. Other questions? Well, if not, then I will see you Monday, Wednesday, Friday, people, tomorrow. I really hope the exams are done tomorrow. I gave them a good long time. But as I said, if you don't get the results tomorrow and able to come and pick up your exam on Wednesday during my 1:30 to 3:30 office hours, then I will at least put up the exam with the answer key so you have something to study from. But we'll get that done just as soon as we can. Good. Well, I wish you all the best on the exam. I happen to think it's reasonably fair. I can tell you this too, there's a lot of extra credit built in on this exam. And if there needs to be a curve in addition to that, then fine, we'll do that. I can't really predict what's going to happen. I never know what's going to happen. But if there needs to be a curve on top of all the extra credit, we will surely do that. Good. Well, like I said, I'll see all of you Monday, Wednesday, Friday, people, tomorrow. And I'll see some of you already on Thursday. So see you all later.